Hello everyone. So this is the lecture number 5 of real analysis. Now let's come to the class topic directly. System of real numbers. So up to the lecture number 4 we have gone through many topics, and I'm giving the links in the description box below. So go through them first. Okay, so real numbers. We know some properties like any number multiplied by 0 is equal to 0. The product of a positive number with a negative number is negative. The product of a negative number with a negative number is positive. Right, we know these things. Sorry. Now, these properties, if you want to prove, means how you go through the examples, like say 2, okay, 2 into 0 is equal to 0, 2 into -1 is equal to -2, right? Or say -2 into -2, that is 4, right? So what I mean to say, to illustrate this property, you will most likely use the natural numbers or integers like we use right now. Even rational numbers also you can use. Then the question is, what are these various types of number? What properties characterize the distinction between these various sets of number, right? So you got it, natural number, you got integers. So when you go for proving this type of properties, then you actually using these numbers, different types of number. The question is that how you will characterize the distinction between these numbers, right? So that is the main objective of this class that we are going to discuss. Now, the system of real numbers has been evolved in different ways by different mathematicians. Some history facts like German mathematician Richard Dedekind, George Cantor, they gave two independent approaches for the constructions of real numbers. At the same time, one Italian mathematician known as G. Piano, he defined the natural numbers by the well-known Piano axioms. Okay, so these are some mathematicians who try to define the real number systems. And about the rational numbers, you already got it that we can construct this type of rational numbers from integers, right? Then, through the set of rational numbers, we reach the stage of real numbers. Then, from this, again, we come into the shape of complex numbers. Don't we will go through the definitions of each of these type of numbers. Real number, you already know. Complex number, we'll discuss. Okay. So, first, one by one. Natural number, we discussed already. How it begins is very difficult to say. But you know that numbers like 1, 2, 3, dot, dot, that they are the natural numbers. Means up to infinity, they are the natural numbers. Okay. Now, we define this as n, capital N. Again, we are not going to include this 0 here, because for that we have integers. In integers, we define the integer set as this one. We have positive integers and negative integers as well, including 0. So if we define the closure property, you might recall it from my abstract algebra class. What is that closure property? Say A and B belongs to a set. I am taking it as say this set integer. Then a operation, say this is the operation being performed between A and B. And if the result of this operation, say C, that is also found to be belonging to Z, then we will call this set is closed with respect to this operation. Right. So if you observe the set of integers, then you will find that this set is closed with respect to addition, multiplication, and subtraction. Then my question is it closed with respect to division? Go and try to find it. Next, rational number. You already know, I have defined it. So if I can express it in the form of what? A by B. A by B. Any number, if I can express in the form of A by B, where B is, of course, not equal to 0, then that number, say C is equal to A by B, that number C is a rational number. These are some examples: 1 by 2, 1 by t, minus 2 by t, minus 4 by 5, 5 by 6, like that. They are natural numbers. Okay. Now, you know the set of Z, that is integer. Here we cannot go for defining or proving that, means we cannot say that this is closed under division, right? So we enlarge the set Z to that of all rational numbers. Okay, so accordingly, we get a bigger set which includes all integers in which division by non-zero integer is possible. And why I am saying non-zero? Because you know that while defining rational numbers, what I am using is A by B, where B is not equal to 0. So no doubt this rational number is a bigger set in comparison to Z, right? Thus, a rational number is a number of the form P by Q where Q is not equal to 0 and P and Q are integer. And this is the general denotation of the set of rational numbers. So Q, X can be written as P by Q, where P belongs to Z, Q belongs to Z, and Q is not equal to 0. Now, simple example. Natural number is a proper subset of Z. Very obvious. Then this set of integers, that is Z, is a proper subset of this rational number. That is also obvious. Now let's come to one question. Prove that there is no rational number whose square is 2. You need to prove that we don't have any rational number जिसका square क्या है 2. Okay. Now we always try to prove this thing by letting the given fact as true. Means say suppose if there is no rational number, we will say that there is a number which can be expressed in the form of square. Then we try to prove that that is wrong. So our concept is, our assumption is wrong. So the given fact is true. Right. Now, if possible, suppose जैसे मैंने कहा कि मैं पहले मान लूंगा कि ये जो रेशनल नंबर है इसको मैं स्क्वायर, इसका स्क्वायर 2 मुझे मिल सकता है, ठीक है, ये मान लेंगे. So if possible, suppose that there is a rational number x such that x square is equal to 2. Now, since you know this x is a rational number, we can express x as p by q, right? Where pq belongs to Z and Q is not equal to 0. Now, integers P and Q may or may not have a common factor. We assume that P and Q have no common factor except 1. हमने ये मान लिया है कि P and Q में कोई common factor नहीं है और of course एक तो सभी में है तो 1 is the common factor. Now, as we are assuming that x square is equal to 2, right? Now, x square means what? P square by Q square, क्योंकि x is equal to P by Q. So, P by Q whole square, that is P square by Q square is equal to 2. So, this means P square is equal to 2 into Q square. Now, from this equation, what we got? P square is equal to 2Q square, right? From this equation, we got that this P square, यहाँ से देखो, P square is even. Yes or no? Because it's the 2Q square that is a multiple of 2. So this P square is even. Therefore, we can write what? We can write this P as 2 into K for some K. ठीक है? Are you getting me? You can write this because we got it. Let me clear this first. Okay. So we can write P is equal to 2K. That thing you got it because we got P square is equal to 2Q square. That is P square is even. So P should be also even. Now we will have P square is equal to 4K square and that is what? Equal to 2Q square. That thing we already got. So that is Q square is equal to, if you consider this part, that is Q square is equal to what? 2K square. Right. So you got that Q is also even. We also got already that P is even. So of course, they will have a common factor. What will be that common factor? If they are both even, then 2 will be their common factor. And this actually contradicts our assumption that P and Q do not have any common factor. So, what is the result or what is the fact we can derive? That what we suppose is wrong. This means the contradiction is, well, we got the contradiction. So that is, there is no rational number whose square is 2. फर्स्ट हमने मान लिया था कि ऐसा रेशनल नंबर है जिसका स्क्वायर 2 है, बट बाद में हमने देखा कि P एंड Q के बीच क्या है, 2 एज ए कॉमन फैक्टर है, बल्कि P एंड Q को हमने ऐसा माना था कि उनके पास 1 के अलावा और कोई कॉमन फैक्टर नहीं, बट वी गॉट इट दैट P एंड Q हैव 2 एज common factor. So what we assume is wrong. So that means we contradict our own assumption. So that, and our assumption is that P and Q have no common factor. So this proves that there is no rational number whose square is true. So we have proved that there is no rational number whose square is 2. Right. Okay, let's clear this. Now, 2 more examples. Try to go through them. So that there is no rational number whose square is 3. There is no rational number x such that x square is equal to 5. Please go through them. Okay. Now, from this example, you may notice that we have some examples, we have some numbers which are not rational, right? And these numbers are called irrational numbers. Those numbers which cannot be expressed as rational number, that is, cannot be expressed in the form of p by q, will be known as irrational numbers. In other words, if it cannot be expressed in the form of p by q, so we can say that this root 2, root 3, root 5, what are they? They are irrational numbers. Okay, so they are irrational numbers. In fact, such numbers are infinite, right? And now you one thing you got, that q is inadequate in the sense that there are numbers which are not rational. So q से भी एक बड़ा एक सेट होगा जो ये सारे जो नंबर्स हैं जिसको हम रैशनली इंक्लूड नहीं कर पा रहे हैं, दैट कैन बी इंक्लूडेड। ठीक है, तो इसके बाद आते हैं हम मेन डेफिनेशन में, एंड लेट्स कम टू द मेन फैक्ट that we want to prove, or we want to actually go through, that a number is which is either rational or irrational is called a real number. So the set of the real number is including every such number which is either rational or irrational. And this capital R is used to denote such set. So R is the disjoint union of the sets of rational and irrational numbers. So if I denote I, capital I, to for these irrational numbers, and you already got Q for rational numbers, then R can be expressed as what? R can be expressed as this Q union or I union, or same thing, I, Q union I. But you know that this Q intersection I is what? Null or void, because there is nothing common in between them. So this thing. So please first note down this fact, that how we are defining these real numbers. Real number R is the set of R is the set denoted by capital R, which is the disjoint union of the set of rational numbers and irrational numbers. Okay. Now consider this line. This line. Draw a straight line like this figure. 0, 1, 2, 3, 4, 5, like that, -1, -2, -0. So choose a point O on L and another point P to the right of L. Associate the number 0 to the point O and the number 1 to the point P1. We take the distance between these points O and P as unit length. We mark such a succession of P2, P3, मतलब एक एक करके बढ़ाते आ रहे हैं हम लोग, बढ़ा के आ रहे हैं, right? To the right to the points like that. Similarly, we can mark P minus 1, P minus 2, P minus 3 like that. 1 unit between them. Now, we can associate every rational number to a unique point of L, right? Let me clear this. Okay. Say we have one rational number 2 by 7, and we want to associate it to a point in L on this line. Then what would happen? 2 by 7 is equal to 2 into 1 by 7. That is, 1 unit is divided into 7 parts, out of which 2 are being taken. Let us see how you can do it geometrically. Okay, sorry. This line you can see, right? 1 unit, but 1 by 7, that is, we are dividing into 7 parts. So 2 divided by 7. This is very clear from this figure 2. Right, A1, A2, A3, A4, A5, A6, A7. Okay, now let's come to the below one. Draw a line OM inclined to the line L. As you can see from the diagram, we mark the points A1, A2, up to A7 on the line OM at equal distance. We have joined P1A. Now, if you draw a line through A parallel to P1A7 to meet the line L in H, then H corresponds to the rational number 2 by 7. That is OH is equal to 2 by 7. Similarly, you can draw the same thing with respect to a negative rational number. Then only thing you need to do, you need to consider the length of L. Right. Okay, this line. So ultimately you have got OH. OH is 2 by 7. Okay. So you try to do it for minus 2 by 7. You try to represent it. Similarly, you try to represent T by 7. You can do it. Now, by having any line through O, you can see that the point P does not depend upon the chosen line OM. Thus, you have associated every rational number to a unique point in the line. Now arises two important questions. Have you used all the points of the line L while representing the rational numbers on it? Of course, the answer is no. You see at the point P, draw a line perpendicular to the line and mark A, this one. So P1A is 1 unit. We cut off OB as equal to OA on the line as shown in this figure. So this OB is equal to OA. Now that B is a point, this B is a point which corresponds to a number whose square is 2. You have already seen that no rational number whose exists for square is 2. In fact, the length OA is equal to square root of 2 by Pythagorean theorem. In other words, the irrational number root 2 is associated with the point B on line L. In this way, it can be shown that every irrational number can be associated to a unique point N on the line L. Thus, it can be shown that to every real number there corresponds to a unique point on the line L. In other words, all the real numbers are represented as points on a line, and is the converse true? That is, does every point on the line correspond to a real number? This is true, but we are not going to probe it here because we are going to explain it in some other future classes. Okay. Okay. Now observe this figure. That what you have to note here is that every real number corresponds to a unique point on this line, and conversely, every point on the line corresponds to a unique real number. And this line is known as real line. This is a real line. Okay. We may define addition and multiplication of real numbers geometrically, like suppose A represents a real number R and B represents a real number S, so that OA is equal to R, OB is equal to S. Yeah, above diagram you can see OA is equal to R, OB is equal to S. Then obviously OC is equal to what? R plus S. AC is equal to OB. Okay. Then the point C is, which is new to the position of B, is defined with respect to R plus S. The construction is valid for positive as well as negative values of R and S. A real number R is said to be positive if R corresponds to a point on the line L on the right of the point O. If it is written as R greater than 0. Similarly, R is said to be negative if it is corresponding to the point on the left-hand side of L. and is written as r is less than or equal to 0. Thus, if r is a real number, either r is 0 or r is positive or r is negative. That is, either is r is equal to 0, r greater than 0, r less than 0. Now you try to construct r minus s, r plus s, r minus s. Very easy, you can do it. Let me clear this. What about the product r and s of two real numbers? We shall consider that both r and s as positive real numbers. So you try to draw the product. ठीक है, प्रोडक्ट को ड्रॉ करने की कोशिश करो आप लोग. Draw O, draw some line OM. Okay, this one. On L, A represents a real number, this S, and OM to a point D, so that OD is equal to R. This is R. And Q be a point on I, such that OQ is equal to 1 unit. Now we join what? This QD. Okay. Through A, we draw a straight line parallel to QD. And what is that? This one. Okay. That is cutting off OP at A. Now, through A, we draw a straight line parallel to QD. That is AC. I just told you that now cut off OP on the line equal to OC. So then P represents, this P represents the real number RS. Okay. Suppose S is a positive real number, R is a negative real number, then there exists a number R such that R is equal to minus R dash, where R dash is a positive real number. Therefore, the product RS can be defined on LS. RS is equal to minus R dash S, so minus R dash S. Similarly, you can state that RS is equal to R minus S this minus R S this. Or S is this is negative, so S is equal to minus S that as this. So that way you can go for proving it. Right. So that's how you can represent R plus R, S, R minus S, and RS on the real line. Similarly, we have complex number. Now, what is this? What is complex numbers? Say you have to find the square root of a negative real number. Say that number is minus 5. Then how will you write it? Minus 1 dot minus root over minus 5. Root over minus 1 into root over 5. But you know that root over 5 is a real number, but what is root over minus 1? Okay. You know that a simple equation x squared plus 1 equal to 0 does not have a solution in the set of real number because the solution involves the square root of a negative real number. And as a matter of fact, the problem is to investigate the nature of root over minus 1, which we denote by I square is equal to minus 1. We claim that I is not a real number. जो अभी हमने देखा I is equal to root over minus 1, and that is not a real number. But say it is real number. For instance, consider say I is real number. Then we have I is equal to either 0 or greater than 0 or less than 0. If I is equal to 0, then I square is equal to 0. And that implies what? Minus 1 is equal to 0. And that is absurd, right? Because you know that I square is equal to minus 1. So that is minus 1 is equal to 0. That is absurd. So this fact we cannot consider. Now, if I greater than 0, we'll get I square greater than 0. That is minus 1 greater than 0. That is again an absurd. Similarly, if I is less than 0, then we will get I square is greater than 0, you know the square of every negative number is a positive. Again, we will get -1 greater than 0. So that is also an absurd. So the fact we have considered, that is I is a real number, is false. So I is not a real number. And this I is known as imaginary number. Okay. And this is known as iota in Greek language, and this generates another class of numbers known as complex numbers. So we again extend the system of real number to the system of complex number. Due to this necessity of finding solution for the equations like x squared plus 1 is equal to 0 or x squared plus 2 is equal to 0. Okay. Now, the first contribution to this notion of such a number was made by the most celebrated Indian mathematician of the 9th century, that is Mahavira, who showed that a negative real number does not have a square root in the set of real numbers. Similarly, some histories are there. I'm not going to concern with that. But to denote complex number, we denote it as C is equal to Z, A plus IB, where A, B are real numbers. And this A is the real part and B is the imaginary part. Any two complex numbers, Z1 and Z2, as Z1 is equal to A1 plus IB1, Z2 is equal to A2 plus IB2, they are equal if and only corresponding this real and imaginary parts are equal. We can add them, we can multiply them like that. In the, say, Z1 plus Z2 will be what? Add the real number part, A1 plus A2 plus IB1 plus B2. Similarly, Z1, Z2 is equal to A1, A2 minus A2, B1, B2, I, A1, B1 plus I2, B2. So the real numbers represent points on a line, while complex numbers are identified as points on that plan. So you can justify that R is a subset of C, because we have actually derived this set complex number by extending it from real numbers. Then some another notifications are there, like algebraic number, like number root over 2. Okay, x square minus 2 is equal to 0. So x is equal to root over 2. So that is an algebraic number. A number is called an algebraic number if it satisfies a polynomial like a n x to the power n plus a1 x to the power n minus 1t, like a n minus 1x plus a n minus 1, where the coefficients a naught to a n are integers, a not equal to 0, n is greater than 1. The rational numbers are always algebraic numbers. The numbers defined in terms of the square root are also treated as algebraic number, but there are some real numbers which are not algebraic, and they are known as transcendental numbers. Like phi, e, they are transcendental number. Okay, transcendental numbers. Okay. So I think that's sufficient. Next class we go for induction, mathematical induction. That's it. Thank you. We'll meet in the next class. Bye-bye.